Cardiac electrophysiology really encompasses the cardiac action potential, depolarization cycle, refractory periods, and the conduction system as a whole. We're going to look at each one of these elements as we go through this presentation. The cardiac muscle cells, cardiac muscle fibers, have some very unique properties. They have these four different properties that you must remember as we go forward in the content. They have automaticity, which is an electrical event. They have the ability to spontaneously initiate an electrical activity. That being said, you could take some of these highly specialized cardiac muscle cells and put them on a table, and they would still have the ability to spontaneously initiate an electrical impulse. Another special property is the excitability. This is another electrical event. This is the ability to respond to an electrical stimulus. So not only can they initiate, but they can respond. Conductivity is another special property, an electrical event. Again, so this is the ability to receive and conduct an electrical stimulus. So we can initiate, we can respond, we can receive it, and we can conduct it, all with the same highly specialized cell. Contractility is the mechanical event, and this is the ability to shorten or contract. This is really true for all skeletal muscle cells and smooth muscle cells, but it's one of the properties of cardiac cells. The other three electrical events are highly specialized for cardiac. As we look at the action potential, this should be a review again from physiology. Electrical impulses are the result of rapid flow of ions back and forth across cell membranes. The big ion exchange and movement is sodium, potassium, and calcium in heart cells, and it creates electrical activity that appears on the ECG as waveforms. When we're looking at potassium, sodium, and calcium, if we have decreased potassium and decreased calcium, we're going to have increased automaticity. If we have increased potassium and decreased calcium, we're going to see a decrease in automaticity. There are certain elements in the ECG cycle called refractory periods. There's an absolute refractory period. This is from the onset of the QRS to the approximate peak of the wave. The cells are depolarized and they can't be stimulated to contract, no matter how strong that stimulus is. And then there's the relative refractory period. This is also known as the vulnerable period, and it corresponds with the downslope of the T wave. Cells can be stimulated if the stimulus is strong enough, and it can result in ventricular chaos, resulting in ventricular tachycardia or ventricular fibrillation. So the relative refractory period, known as the vulnerable period, is a very sensitive spot, and it's denoted by the blue bar on our slide. Here's another picture of the main refractory periods. The absolute refractory period starts with the beginning of the QRS and goes to the upslope of the T wave. And the latter portion of the T wave is the relative refractory period. And you can see that denoted here. The relative refractory period is a very vulnerable zone. Looking at the conduction system, we're going to cover all of the different elements of it. The sinoatrial node, or the intranodal pathways, the atrioventricular junction, the bundle of His, or the His bundle, the right and left bundle branches, and then the Purkinje fiber network. You can see here the SA node is the starting point. The impulse travels to the AV node. Then it travels to the His bundle, where it does a little pause before heading down the right and left bundle branch and then to the Purkinje fibers, which will then complete the entire electrical conduction system. We're going to look at each one specifically now. So the sinoatrial node is located at the junction of the SVC, or the superior vena cava, and the right atrium. It's right at the top of that atrium. It initiates electrical impulses at a rate of 60 to 100 beats per minute. That is the inerrant rate of the SA node. It's an important piece of information. Normally, this is considered the primary pacemaker of the heart. The AV junction is the area of the AV node and the bundle of His down to the branch of the right and left bundles. The function here is to delay the impulse and allow the atrial contraction to really occur, causing the atrial kick, and then complete the filling of the ventricles as the atria eject the last of their blood. It's the first escape pacemaker of the heart, meaning if our SA node fails us, hopefully our AV junction will take its place. The inerrant rate of the junction is 40 to 60 beats per minute, another very important piece of information. The bundle of His or His bundle is the electrical connection between the atria and the ventricles. It conducts impulses between the AV junction and the right and left bundles. The right and left bundle branches travel down that septum that divides each of those two ventricles. And one of them, the left bundle branch, divides into 3 different fascicles as it travels up. Remember that left ventricle is the bigger piece of muscle, the bigger workhorse of the heart, so it requires a little bit more electrical outreach, so to speak. The Purkinje fibers are the web of fibers that penetrate into the ventricle muscle itself. It receives impulses from the right and left bundle branches, and then it conducts those to the rest of the ventricles themselves. The ventricles can be considered a second escape pacemaker. And the inerrant rate of the Purkinje fibers, or the ventricles, is 20 to 40 beats per minute. It really is the least desirable of all of the different pacemakers of the heart, because a heartbeat of 20 to 40 probably wouldn't sustain you very long. We would hope that something else would help us out before that. But in the event that this is all we got, we'll count on those 20 to 40 beats per minute. If you have any questions on this content, please post them to the Raise Your Hand forum on our Blackboard site.